Application-specific hardware accelerators are generating a lot of excitement right now. These chips can enable far more energy-efficient computing than more general-purpose CPUs and GPUs. However, it can be quite challenging to build one of these accelerators. As a result, there's a lot of interest in making it easier to build more efficient custom hardware solutions. In this talk, I'm going to focus on one important aspect of building accelerators: navigating the trade-off between performance and resources. Chips are designed to meet a performance target. However, increasing performance will increase resource requirements. Designers must set a resource constraint to ensure that a chip fits in the target device, such as a phone. As an example of this trade-off, let's consider an accelerator that implements a convolution on a stream. This accelerator computes the average of the last 3 elements that have arrived. It's performing the same computation as the expression above it. When running on an input stream like this set of 6 elements, the first 2 elements of the stream are gonna get shifted into registers in order to store them on the chip. When the third element arrives, the circuit is now going to compute an output using all 3 elements that it's seen. The bottom adder computes the sum of the elements with values 1 and 2. Then the top adder computes the sum of 0 and 3. And the divider emits the circuit's output. This repeats every clock so that for every new element in, the circuit produces 1 element out. Notice that this circuit requires 2 adders and 1 divider worth of resources. If the designer wanted more performance, they could add more resources with more adders and more dividers. This circuit on the bottom can accept and emit 2 elements per clock. Conversely, if the designer only wanted to use 1 adder and 1 divider, they could create a circuit that emits only 1 element every 3rd clock. In the bottom circuit, the adder is used every clock, but the divider is red to demonstrate that it's underutilized. It's only used every 3rd clock. The 3 convolution circuits all compute the same thing, but all require different amounts of resources and have very different wirings. So I've talked a lot about what boxes to put on the screen for the circuit diagrams, but I haven't focused on the lines between them. An important aspect of hardware design is how these components know when their inputs are ready. One solution that works generally is to have a handshake where consumers wait for the upstream producers to emit values. This dynamic communication requires more resources and yields lower clock rates. A better solution is to ensure, at design time, that all modules in the circuit communicate on exactly the right clock cycles so that interface timings are statically scheduled and dynamic behavior is not necessary. In this talk, I'm going to present Aetherling, type-directed scheduling of streaming accelerators. It's a system for producing efficient, statically scheduled accelerators and enabling designers to explore the space of trade-offs between performance and resource utilization. Oh, by the way, I'm David Durst. You'll see me pointing at key ideas throughout the talk. Aetherling makes 2 main contributions. The first contribution is the space-time IR, which describes the semantics of hardware accelerators and has a type system that statically encodes when operators communicate data. Programs that type check in this IR can easily compile to statically scheduled hardware. Aetherling has a second language called the sequence language. This language is a fairly standard functional language that encodes the semantics of hardware accelerators, but not the timing of interfaces. Aetherling's second contribution is a set of rewrite rules to convert from the sequence language to the spacetime IR. Developers write in the sequence language, and a scheduler searches over the rewrite rules to automatically compile high-level programs to circuits with different trade-offs between performance and resource utilization. We call this compilation step scheduling because it determines the timing of how a program executes in hardware. Let's start by looking at the sequence language. It's a fairly standard data parallel language that has map, reduce, and a few extra operators for image processing like downsample, which takes 1 element out of a sequence and drops the rest. The most important property of this language is that operators process fixed-length sequences. The lengths of all sequences are statically known at compile time and incorporated into dependent types. As an example, imagine that I've defined a function that adds 10 to an integer. I can map it to apply the function to a sequence of elements. The type signature of the map is a function on a sequence of ints. This signature encodes that the length of the sequence is 4. The sequence language describes what to compute, but doesn't completely specify the properties of the hardware used to do the computation. We have a second language, the spacetime IR, which will describe the hardware's interfaces. Here's one circuit that we could describe in the spacetime IR. This circuit processes 2 elements at a time over 2 clock cycles. These boxes are the input and output sequences. The numbers in the boxes are the circuit's input and output values. The circuit diagram shows parallelism by placing the space dimension on the y-axis and the time dimension on the x-axis. Time flows right to left, so the first stream inputs are 0 and 1, and the first outputs are 10 and 11. The first key idea of Aetherling is that the space-time IR types describe the timing of hardware interfaces. In particular, the types describe the throughput and per clock cycle I/O. All space-time IR operators have an interpretation as hardware. For example, there are 2 versions of the map operator in the IR. The map-S, or map in space operator, describes a fully parallel accelerator that processes all elements in a single clock cycle. The circuit diagram shows a 4-element per clock circuit. 4 elements arrive on the same clock, map-S adds 10 to every element, and the 4 elements depart on the same clock. The type signature of map-S specifies the circuit's timing behavior. sseek4int, or spaceseek4int, is a sequence where all 4 elements occur on the same clock cycle. Aetherling can also use map-T, or map in time, to describe a fully sequential accelerator that processes all elements on separate clocks. The circuit diagram shows a 1-element per clock circuit. The 4 elements in the stream arrive on separate clocks, are processed one at a time, and depart on separate clocks. The type signature of map-T specifies the circuit's timing. tseek4int, or timeseek4int, is a sequence where all 4 elements occur on different clock cycles, one after another. Please hold off on the 0 in the tseek type. I'll explain that in a second. Space and time operators are Aetherling's main ways for specifying circuits, and the operator's space and time sequences encode their timing behaviors. While we've seen the core building blocks of Aetherling, we have only explored a subset of their expressive power. Aetherling's operators and types enable the expression of a far richer space of circuits than just fully parallel and fully sequential ones. In order to express circuits with a throughput of less than 1 element per clock, Aetherling temporal operators can be underutilized. Their interfaces may communicate no information for some invalid clock cycles. This map-T has 4 valid clocks followed by 1 invalid clock. The type signature of this map-T encodes this pattern of valid and invalid clocks. tseek's second parameter indicates the number of invalid clocks following the valid ones. While this may seem like a waste of hardware for the simple example of map add 10, the ability to represent interfaces that go idle is necessary for some operators like downsample, which remove elements from a sequence. Aetherling uses nesting to express partially parallel circuits with throughputs in between fully parallel and fully sequential. The composition of map-T and map-S defines a circuit that processes 2 elements per clock. The resulting type signature contains nested tseeks and sseeks that encode the partially parallel interfaces. Combining nesting and invalids enables Aetherling to describe a rich set of interfaces. For example, in the bottom here, I showed that by nesting 2 tseek types, Aetherling can describe a repeated pattern of 1 valid clock followed by 1 invalid clock. Thus, composition of space and time types enables Aetherling to statically encode a wide range of circuit interfaces. Clearly, if we can perform this encoding with types, then checking a circuit's timing behavior reduces to type checking. This is our second key idea. If a program type checks, Aetherling can compile it to a streaming hardware accelerator with statically scheduled interfaces. Let's see this in action with a simple example. This circuit adds 10 to 2 elements per clock, then adds 10 again to those elements. As we can see from the circuit diagram, the input and output types all match. All are tseek20 sseek2int, so the program type checks and Aetherling can compile it to a circuit where the first mapped add 10 produces 2 outputs per clock that are immediately consumed by the second mapped add 10. A more involved example of statically checked timing behavior includes space-time IR operators with different input and output throughputs. In this circuit diagram, the accelerator downsamples the input and then adds 10 to every remaining element. The downsample accepts 1 element per clock and emits 1 element every other clock. To enable static scheduling, add 10 must match downsample's output throughput. Map with invalid clocks accomplishes this. So we've seen the sequence language for describing timing unaware semantics of circuits, and the space-time IR for describing the timing behavior of the circuits. The last key piece of Aetherling is its rewrite rules for going from the sequence language to the spacetime IR. The third key idea is that Aetherling can explore a large space of performance resources trade-offs using a simple set of rewrite rules. Of course, there are rules that take sequence operators to their parallel and sequential versions, such as rules for map to map S and map to map T. To generate partially parallel spacetime IR programs, Aetherling includes a standard rule that splits maps into nested maps. By first applying the nesting rewrite rule, and then the fully parallel and fully sequential rules, a sequence language map can be converted into a partially parallel spacetime IR program which compiles to the circuit at the bottom of the screen. Overall, Aetherling's rewrite rules are pretty simple. Most sequence language operators just have these three rules for fully parallel and fully sequential circuits along with nesting. Different choices of rewrite rules correspond to mapping a sequence language program to different circuits with different resource requirements. The last piece of Aetherling is a scheduler that selects rewrite rules to automatically compile programs from the sequence language to the spacetime IR. We refer to the process of picking rewrite rules as scheduling, since it determines how a program executes in space via parallelism and time. The inputs to scheduling are an Aetherling program in the sequence language and a target output throughput of t elements per clock. The scheduler uses two important features of the spacetime IR. First, key idea 1, that types encode throughputs, and second, since our operators are really simple, we can approximate the amount of resources required by programs built out of the operators. With these features, the scheduler is able to find a combination of rewrite rules that produces a spacetime IR program with the target throughput and limited resource utilization. Since types encode throughputs, the scheduler just has to search for a spacetime IR program with the right types. The search is guided by the resource utilization approximation. When the scheduler finds a program with the correct spacetime types, the key ideas ensure that the resulting spacetime IR program will compile to a statically scheduled circuit with the expected throughput. I won't dive into the details of the scheduling algorithm. The details of this heuristic-driven search are in the paper. Let's look at how well Aetherling does in practice. We evaluated Aetherling using a suite of benchmarks from the image processing domain. These range from 2D convolutions to a simple raw camera pipeline. We evaluated our designs on HD images and compiled them to a Xilinx FPGA. Remember, one of Aetherling's goals is to explore a large space of performance resource trade-offs for a single sequence language program. For our three apps, we compiled a single sequence language program to a range of statically scheduled accelerators with throughputs between 1/4 and 16 pixels per clock. The only exception is camera, as it wouldn't fit on the target FPGA at higher throughputs. The x-axis shows the throughput of each design, and the y-axis shows the resource requirements of these designs in units of FPGA slices. Slices are the resource used for simple math, like addition, as well as overhead of control logic used to manage dynamic communication between and inside operators. Both axes are log scale, and so across all these applications, we see a linear relationship between performance and resources. The only exception is at throughputs less than 1 element per clock. The high resource utilization here is due to control logic overhead inside underutilized operators. We also measured two other types of FPGA resources, BRAMs for storing large chunks of data like rows of images, and DSPs for doing complex math like division. These charts also demonstrate the performance resource trade-off. In addition to facilitating design space exploration, another of Aetherling's goals is to generate efficient statically scheduled circuits. To demonstrate the benefits of static scheduling, we compare Aetherling to Spatial, another programming language for building accelerators presented at PLDI 2018. The x-axis shows the throughputs of the designs, the y-axis shows the slices used by Aetherling's designs relative to those of Spatial. Since Spatial is a more general-purpose system, it relies on dynamically scheduled components. Aetherling's designs use 1.8 to 7.9 times fewer slices than Spatial due to their static scheduling. Aetherling and Spatial use similar amounts of BRAMs and DSPs. There's a lot of prior work on making it easier to build efficient hardware accelerators. Research ranges from HLS to synchronous data flow. I'd like to draw attention to two subfields of that work. Data flow-based systems like SDF, as well as recent work built on top of it like Ripple, have goals similar to Aetherling's for scheduling accelerators. They differ from Aetherling in how they accomplish these goals. Aetherling uses a type-directed approach rather than an out-of-language solver. This type-directed approach is similar to Clash and Lift, which uses types and rewrite rules to schedule hardware accelerators. Aetherling extends these type embeddings to encode more precise timing behavior that was necessary to produce statically scheduled accelerators. In conclusion, the goals of Aetherling are to produce statically scheduled accelerators and explore the space of performance resources trade-offs. The key ideas of Aetherling that accomplish this are that types describe the timing of hardware interfaces. If a program type checks, Aetherling can compile it to a streaming hardware accelerator with statically scheduled interfaces. And Aetherling can explore a large space of performance resources trade-offs using a simple set of rewrite rules. These key ideas demonstrate the opportunity for programming language concepts to aid the development of hardware accelerators. Through techniques like encoding properties of accelerators and types, we can enable a faster iteration loop for expert designers and make hardware design accessible to a broader group of individuals. Thank you. Aetherling is open source and available at aetherling.org.